Alright, so we're going to kind of dial in more with covalent molecules here. And so there's two versions. But before we talk about the molecules, we got to talk about the bonds. So I wrote polar versus nonpolar covalent, and I realized, like, oh, I got to specify bonds because we're going to break out molecules later. So this is just what's happening with the shared electrons between two atoms, not the whole molecule, just like one spot. And then we'll build on that for the rest of it. So we have to have all nonmetals, so covalent, that definition hasn't changed. It's all nonmetals. They can't steal the electrons from each other. They're all too good. They're all masters of tug of war, but some are better than others. And so we can have an uneven sharing of electrons, and that gives us a polar bond. So I should also add, covalent equals shared electrons. Well, polar bond is unevenly shared electrons. So I'm going to abbreviate as E minus because life is great with shortcuts. So if you have unevenly shared electrons for a polar bond, you might never guess what a non-polar bond is. So you have evenly shared electrons. It's that simple. So if it's non-polar, they're all evenly shared. And so what happens is if you don't share electrons evenly, they hang out on one side more than the other. Maybe they got something like this. You've got a region over here where the electrons are shading more this way. Well, that's going to mean that over here is a little more negative, and over here is a little more positive, because where the electrons aren't is positive, and where the electrons are is negative. And so it's kind of a miniaturized version of ion, where it just gets fully ripped from one side to the other. Well, it doesn't get pulled completely over, but they're shading a certain way. And so that creates a positive and a negative pole, gives you a polar bond. And then this joke always kills when I tell it to class. No one ever rolls their eyes, but you've got, what do you call a bear that has unevenly shared electrons? It's a polar bear, obviously. Whereas if it does evenly share its electrons, well, you have one of those non-polar bears. So, I don't know, a black bear or something, brown bear, whatever it might be, a panda bear. Panda bears definitely share their electrons equally. They're not polar at all. Alright, so, like three people are laughing somewhere in the world because of that. And that's good enough for me, because that's 3 times what a class normally does. Alright, so how do we know if something's going to be polar or non-polar? Alright, so this is where we break it down. And so again, we're still just talking about bonds. We haven't gotten to molecules yet. So, if you have the same element on both sides of the bond, like I had hydrogen before, they have exactly the same electronegativity. They're going to fight just as hard for those electrons, and so they're not going to hang out on one side more than the other. They're going to evenly move back and forth. So they're going to be fairly shared. Fairly shared through force. That's what's going to happen. It's not like it's out of the kindness of the atom's heart. So if the bond has both atoms, so there's always two atoms associated with a bond. And if they're both the same element, then it's going to be nonpolar. Okay? So, for example, hydrogen bonded with hydrogen. Remember, these lines in a Lewis structure mean a bond. Or, this isn't a full structure for a molecule, but if you have something like carbon bonded with carbon, chlorine bonded with chlorine, these are all going to be nonpolar. Now, there's one more situation where it's nonpolar. And that is when carbon is bonded with hydrogen. And that's because their electronegativities just happen to be really close in value. So here's kind of the one weird exception you got to remember. So if you see the same element paired with itself, they're going to share electrons evenly. If you see carbon bonded to hydrogen, they're going to share electrons equally. And this is going to be really important for organic chemistry because there's a ton of these kinds of bonds in organic molecules. So organic chemistry is the chemistry of carbon. And so there's a lot of carbon bonded to carbon, but there's also a lot of carbon bonded to hydrogen. And sometimes you get some nitrogen and oxygen and stuff worked in as well. But there's a ton of hydrogen and carbon in there. And so there's a lot of nonpolar bonds that follow this little specific situation. So I got to tell you about it. Now, if it's anything else, you know, any other two nonmetals, that are not the same, we'll say mismatched. Well, that's going to be polar because you have a mismatched electronegativity. So for example, if I have fluorine bonded to carbon, they don't have the same electronegativity. Fluorine is going to be more electronegative than carbon. That's going to be polar. Now if you have so it's got to be two nonmetals or else it's not covalent, but it has to be a mismatch that's not carbon and hydrogen. So you see a pair, nonpolar. You see carbon and hydrogen, nonpolar. So that's the weird one you got to remember. Anything else that's mismatched, carbon and fluorine, nitrogen and chlorine, phosphorus and sulfur, so on and so forth. Anything like that. A bond between two nonmetals that aren't the same, with that one exception, and you have a polar bond, okay? And so these aren't sharing electrons equally. And so the electrons are going to be more towards the side of the bond with the more electronegative element. So here, they're equally shared, so they're just kind of, you know, moving back and forth freely. They're just as much on the left as the right. Things balance out. Look at carbon and fluorine. Well, as I mentioned earlier, fluorine is to the right of carbon. It's more electronegative. So the electrons are going to shade towards the fluorine more, making this polar bond. So the carbon is going to be slightly positive, and the fluorine is going to be slightly negative. And here's how we label this. You do a little arrow. The arrow points to where the electrons are hanging out the most. And it has a little plus on the tail because whatever's left behind is slightly positive. And we call this a dipole arrow. So this is how we label polarity. And you can do this for molecules as well, but we're just starting out with bonds. We're real close to getting to molecules. But that's what we're looking at. Alright? So, now let's start talking about molecules. And before we get into it too much, we're going to talk about the Lewis structures. And then we're going to talk about labeling polarity. And we're going to bring that dipole arrow back. Okay, so we had Lewis structures for atoms. Now we're going to do Lewis structures for molecules. Now the first thing to remember is that an element, specifically, you know, a non-metal element, right? If it's a metal, we're not getting a molecule. We're getting an ionic compound. It's going to make a number of bonds equal to number of electrons needed to fill the valence shell. And so guess what we use to help us out with this? You don't have to memorize what every element needs to fill its valence shell. How many electrons does it need? You just look at your periodic table. How do you know to look at your periodic table? I literally already had it on camera, right? That's a pretty good clue. So, if we look at this, you guys are going to love that squeaky chair all quarter. You're welcome. I try to sit forward on it, but sometimes I just, you know, I get so relaxed talking about molecules, I just have to lean back. Alright, so hydrogen, we talked about this before, needs one one electron to fill its valence shell. That means it's going to make one bond. But if we look at something like carbon, so carbon's very versatile. We can talk about that right now. It has 1, 2, 3, 4. It's a non-metal, but it needs 1, 2, 3, 4. So it needs 4 electrons. Well, guess what it does? It makes 4 bonds. Alright, now here is what happens. So let's look at CH4. How do you know it's CH4? Because I told you it's CH4. So what that means is there's 4 hydrogens. So we have 1 carbon atom. And 4 hydrogen atoms. And they're going to make a covalent molecule. Now, when you see something like this, generally whatever makes the most bonds goes in the middle. So I'm just going to start with carbon. I'm going to draw this in a very strategic way. I'm going to draw the atoms first. And then I'm going to have a hydrogen here, a hydrogen here, hydrogen here, and 1 here. So the carbon gets 4 dots because it has 1, 2, 3, 4 valence electrons. Hydrogen has 1, so it gets 1 dot. Now, hydrogen needs 1 more electron, so it makes 1 bond. Carbon needs 4 more, so it's going to make 4 bonds. Now, these valence electrons, in order to make a bond, both sides have to kind of pitch in. So, carbon's going to throw an electron in, hydrogen's going to throw an electron. So a bond is made out of 2 electrons, and it's 1 from each atom. So they throw in together. And so what that means is I'm going to connect the dots. Okay? Like so. And so now, when I look at my valence shells, I count bonded electrons for carbon, but I also count them for hydrogen. And so if I look at this hydrogen, it has 2 electrons in this bond that's attached to it. That means this hydrogen has 2 bonds. It has a full valence shell. This one up here, 2 electrons, full valence shell. 2 electrons, full valence shell. 2 electrons, full valence shell. But I get to count those bonds again when I look at the carbon. It has 2, 4, 6, 8 electrons. And guess how many electrons carbon needs? 1, 2, 3, 4, 5, 6, 7, 8 electrons. So it has filled its valence shell. So that's what carbon does. Carbon's going to make 4 bonds to fill its valence shell. If we look at something like nitrogen, it needs 1, 2, 3. It's going to make 3 bonds to fill its valence shell. So it'll have some electrons left over that don't bond. So if we look at something like NH3 as another example here, that means we're going to have 1 nitrogen, 3 hydrogens, just like we'd have 1 carbon and 4. How do you know? I gave you the formula. Alright, I'm going to start with nitrogen. And remember, it's going to have 5 valence electrons. So I'm going to have a pair of 2 and then 3 by themselves. And you know, you might not have decades of experience doing this, so you might not put your dots as neatly together as I did. But that's what the atoms look like. And then this is an unpaired electron. That's an unpaired electron. So they're going to make bonds. These 2 are already paired, so they don't need to make a bond. So what we're doing is we're surrounding our atoms with paired electrons. And again, hydrogen on left, 1, 2 electrons. Hydrogen on the bottom, 1, 2 electrons. Hydrogen on the right, 1, 2 electrons. Nitrogen in the middle, 1, 2, 3, 4, 5, 6, 7, 8. So it doesn't need to make 4 bonds to get 8 electrons around it. Okay, so now let's bring polarity back into the picture. We're going to play around with Lewis structures more. We'll practice it on the next sheet some more. But let's look at CH4. Now, if you remember the last page, you might already know the answer. But are these carbon-hydrogen bonds polar? And the answer is no. They're that one exception, right? They're the one that has similar electronegativity. Every other mismatched pair of nonmetals will be polar. And so what we have is this is all nonpolar bonds. There's no dipole to label. There's nowhere we can draw an arrow because they're all equally shared. And so that means that we have a non-polar molecule. Alright? That's a key idea. So there's no uneven electron sharing in this molecule anywhere. There's no, hot and cold area, no slightly positive, slightly negative. It's all evenly shared. So it's all nonpolar bonds that cause that to happen here. And so that's a nonpolar molecule. There's one more way to get a nonpolar molecule. We're going to talk about that. But next, let's look at this NH3, which, if you don't know what these are, this is methane, CH4. This is methane. That's natural gas. So if you've ever used a natural gas furnace or fireplace or stove, you've seen this get lit on fire. Congratulations. You've seen a reaction involving this compound. This here, NH3, is ammonia. So it's somewhat, it's not as common of a cleaner as it used to be. It's pretty harsh. It smells terrible. If you have a neighbor that has too many cats, and you know that smell that you get when you have too many cats? You're smelling ammonia. So you know what ammonia is. Every now and again I teach labs that use ammonia, and if someone leaves that bottle open, or if they take it out of the fume hood and don't put it into another fume hood quickly, everyone in the room knows, because everyone smells disgusting ammonia. Yeah, everyone gets to be the one that causes the smell of shame. Okay, so are these polar bonds? And the answer, hopefully you know this, is yes, because nitrogen and hydrogen are not the same element, and they are not carbon and hydrogen. And so this is a polar bond, this is a polar bond, and this is a polar bond. And so we can label these, right? Now what's more electronegative between nitrogen and carbon? So before I finish labeling, let's look at the periodic table. Or sorry, between nitrogen and hydrogen. Well, remember, hydrogen and carbon are like a tie. So you can cheat a little bit with hydrogen. And you can just be like, well, where's carbon? Oh, okay. Well, nitrogen's more electronegative than carbon, so it's going to be more electronegative than hydrogen. And so the electrons are going to shade towards the nitrogen, and the hydrogen is going to be slightly positive charge. Same deal over here. And this guy. And so what we have are two arrows that cancel each other out, right? They oppose each other. They oppose each other. It's like they don't happen. But we have one that does. And so what we have is a net dipole. Because remember, these are called dipole arrows. And those dipole arrows, that's an arrow, by the way, that's an arrow pointing to the dipole arrow. We have reached arrowception. We've done it. But because they are equal and opposite, this is going to be the same magnitude as this because it's the same bond, but they're on opposite sides, so they're going to cancel out. So I'm going to be like, hey, yeah, okay, that cancels, that cancels. There's nothing up here to cancel this dipole. So that gets me a net, what we call a net dipole, excuse me. And so that means that we have a polar molecule. Alright. So if the dipoles don't cancel out, you get a polar molecule. So there's two ways to get a nonpolar molecule. And this is the first one up here with the CH4. If it's all nonpolar bonds, you don't have any uneven electron sharing. How can you have a polar molecule if you don't have any uneven electron sharing? If you do have uneven electron sharing, you could have a polar molecule if that unevenness doesn't completely cancel out. So let's look at one more example here. Always in the news here, CO2, carbon dioxide, very important biologically, and it turns out, as we've learned in the last, since the industrial age has started, well, not right away, but we started figuring out around the 60s at least, that it is important environmentally as well. So CO2, we're going to have one carbon and two oxygens, right? So I'm going to draw my carbon. dot, dot. And feel free to pause, take a shot at this yourself. This one's going to be a little tricky. There's a trick in this one I haven't shown yet. Just a heads up. Okay, and then we haven't shown oxygen on the periodic table yet, but it's going to have 1, 2, 3, 4, 5, 6 valence electrons. So I got to put 6 dots around it. Okay, so I'm going to draw an oxygen on the left, an oxygen on the right, or I guess on the right and on the left, whatever. Okay, I'm going to go dot 1, 2, 3, 4, and I'm going to actually do this 5, 6. I'm going to bounce back. So I got an unpaired, unpaired, pair, pair. And I'm going to do a pair down low, pair in the back, 1, 1. And I did that just to make my life easier. Okay, and so now I'm just going to start connecting the dots. I'm going to connect all my unpaired electrons. I'm going to make pairs out of them. Okay, and that's what we get. And so we can do this. And there's another way to write this just a little bit cleaner. Like so. And so what this is what we call a double bond. Again, we are so creative with the names, right? So creative. And by the way, these electrons over here, we call these lone pairs. So these are bonding electrons. Each one of these lines represents 2 electrons. So we call that a bonding pair. And if it's not there, it's a lone. We call it a lone pair. So there's 2 lone pairs on this oxygen, and then there are 2 bonding pairs as well. And on the oxygen on the right, there's 1, 2 bonding pairs, and then a lone pair and a lone pair. Could have drawn these dots a little close together, but these dots are on the bottom. They're paired. Sorry about that. I left my Sharpie eraser in the office. That's what it is. Okay, so if I count up the electrons, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons around this oxygen. And this carbon has 2, 4, 6, 8 electrons, so it has a full valence shell. This oxygen has 2, 4, 5, 6, 7, 8 electrons. So they all have full valence shells. So we can have single bonds, which is what I showed before. It's just a single bond. We can have double bonds, and we can also have triple bonds. There's no quadruple bonds. Now, actually, someone has done that, but it's a very special circumstance. We're not going to worry about it. Very unique. I think they used Rutherfordium for it too, which came up in the last previous video where I was making fun of it. So someone actually did something with that one. But don't worry about it. So we get single, double, or triple bonds. It's really hard to fit more electrons than that in this space because they don't like being around each other. And carbon's not going to do a quadruple bond. It'll never do a quadruple bond. It'll make 4 bonds, but it could do 4 singles, double, double. It could do a double, 2 singles, a triple, and a single. You know, it has options. That's what drives organic chemistry. Carbon can do a lot of different bonding things. So this is one example. Now, is it polar? And those lone pairs can be organized however, it doesn't matter. As long as there's 2 bonds here, 2 bonds here, and 2 lone pairs, doesn't matter. I'm just not rearranging them because I want to keep it consistent. But we look at this molecule, we go, is it polar? Is it nonpolar? Well, let's draw some dipole arrows. So what's more electronegative here? We've got oxygen, we've got carbon. Carbon is to the right, oxygen is to the right of carbon. Oxygen's over here, more to the right. Carbon is to the left of oxygen. They're both nonmetal, so they are sharing electrons, but they're not sharing them equally because they're not the same element. It's not carbon and hydrogen, it's carbon and oxygen. So there's unequal sharing, and it turns out that oxygen is going to hog the blanket on this one. It's going to be hogging the electrons. So we're going to have an arrow that points from the center to the right with a positive tail. We're going to have an arrow that points from the center to the left with a positive tail. Well, guess what happens here? Think back to what I talked about with the ammonia. It had a left and right. These dipoles cancel. So there's two polar bonds, but they cancel each other out. You have an oxygen trying to pull everything right, you have an oxygen trying to pull everything left. Guess where it gets stuck? Right in the middle. So, dipoles cancel. Non-polar. I should say non-polar molecule. So to be clear, that's a polar bond, and that's a polar bond. But dipoles cancel, non-polar molecule. So if you can draw a Lewis structure of a molecule, you connect the dots, and the dipoles cancel, it's a non-polar molecule. This is tricky. I have to talk about one exception. There's a lot of exceptions to this because there's a whole bunch of stuff I'm not talking about with the shape of molecules. There's one I have to talk about. So I have to be very careful in how I draw Lewis structures. But before I talk about the exception, let's kind of practice this a little bit. I want to make sure that this makes sense before I talk about the weird thing that I can't avoid. If I could avoid it, I would. I avoid so many other weird exceptions, but I can't avoid this one, and you'll see why when I talk about it. But for practice, let's look at CL4 and CL3 with a hydrogen in there. So in both cases, the carbon is going to be our central atom. So be aware of that. It's going to start with carbon. All right. And so I'm going to go carbon because it makes the most bonds out of all of these. How do I know it makes the most bonds? Bam! Periodic table. That's how I know. Look at chlorine. It needs 1 electron. Okay. There's only going to make 1 bond. Hydrogen needs 1 electron. Only going to make 1 bond. Carbon needs 4. It's going to make 4 bonds. And if you see carbon, it's going in the middle. Nothing's making more bonds than carbon. Not in my class. Not on my watch. No, sir. There are things that do that, but again, we don't talk about the stuff that lets that enter the conversation. So carbon makes the most with 4 bonds in this class. Alright, and so I'm going to draw 4 chlorines. It's going to get 7 dots. I'm going to strategically place my 1 unpaired electron facing the carbon. Okay. And I'm just going to do that over and over again until I've drawn 4 of them. So there we go. Alright, what do? We connect the dots. Alright. Now, I think your book might do a notation. I forgot to mention this earlier. But it might just show 2 dots in between. That's one way of doing it. Lines are faster to draw. Lines are how the pros do things. Alright, and so let's draw this guy next, the CL3H. So carbon's in the middle. I'm going to have 1 hydrogen, a chlorine, and you can put the hydrogen on any side. As long as there's 3 chlorines and 1 hydrogen around this, it works. So the hydrogen could be on the left or up or down. As long as the other 3 spots are occupied, you're good. And then we just connect the dots. Boom. Oops, I left a dot off. There it is. There. It was there the whole time. Line, line, line. So we have 4 single bonds, 4 single bonds. Okay. Are these polar? Well, we've drawn our Lewis structures. Does this have polar bonds? Yes, so it could be polar. We're going to whip out the periodic table here. And it turns out that chlorine, I told you I wouldn't do diagonals, but chlorine is more electronegative than carbon. It's very far to the right, it's only down 1, so this trend left-right is much stronger than the up-down. And so it's going to have dipole arrows like so. And I'm just going to draw them next to every bond. Arrows are going to point at the chlorines, have a positive tail by the hydrogen, or by the carbon. Oh man. This video is getting long. I can't say my elements. Alright, and so that means that we have one that goes right, that's going to cancel with one that goes left. We have one that points up, we have one that points down. So these all cancel out because they're all carbon-chlorine bonds, they're all equally strong. Equally strong up and down, like it doesn't happen. It's gone. Left and right, cancel out like it doesn't happen. So this is a non-polar molecule. Okay. Over here, well, we've got this, but what about this bond? I'm sure you all remembered carbon and hydrogen is non-polar. They just happen to have very similar electronegativities. And so we have a down that cancels with an up. You look at that right there, that's a net dipole. This is a polar molecule. Okay, so as long as those arrows don't cancel out in terms of up, down, left, right, and there's no way to, if there's any way to arrange them where they don't cancel, then they don't cancel. As long as you're, equally spacing stuff around. So that's kind of the trick. So are these polar or not? So let's talk. There's one more thing I'm gonna do in this video. Man, it got long. So we've talked about a lot, and I'll kind of talk about one more thing. So if you can cancel those arrows, it's non-polar. The exception, and I cannot avoid this exception. This molecule is too important. It's water, which is H2O. Okay? So hydrogen makes one bond, oxygen makes two. Oxygen is going to be my central atom. It has 6 valence electrons from my periodic table. We talked about this before, but you can count it out left to right. You go 1, 2, 3, 4, 5, 6. Okay? And I can write them any way I want, so I'm going to keep the unpaired on the left and the right. And then hydrogen, which we've done a lot of examples with, has 1 dot, 1 valence electron. And now I'm just going to connect the dots. Okay? Are these bonds polar? Yes. Hydrogen, you can use carbon like a placeholder. Oxygen's to the right of carbon because these two are basically a tie. So oxygen is more electronegative. And so I'm going to get arrows that look like this. Right? And so you're like, oh, non-polar? And it turns out that water is a polar solvent. So it breaks the trend I talk about, breaks the rules I laid out for the class. There's more to the shape of molecules than I talked about. This is the only exception, and you just got to know it, because water, I don't know if you know this, is really important for biological systems. We're essentially water balloons walking around. Your water balloon's learning chemistry right now. You are some of the smartest water balloons in the history of the planet, and you're still water balloons. Okay, our cells are just little bubbles filled with water, kind of like soap bubbles almost. So it's a polar molecule. Don't tell Paul I said all that, by the way. Paul doesn't need to know my biology facts. He'll probably be like, oh, they're really important in the essence of everything, and I'm gonna go, nah, they're just like soap bubbles that reproduce, whatever. That's how a chemist views a cell. Alright, so why is it a polar molecule? Well, these lone pairs on the oxygen cause it to have a bent geometry. So the hydrogens aren't straight across from each other. So the dipoles aren't directly opposite, so they don't cancel. Now your normal up, down, left, right stuff isn't going to show that. So again, this is the only exception that I'm going to hit you with in this class. You just have to know, because we're going to do so much stuff with water. So dipoles don't cancel equals polar molecule. And this is so important for water. The fact that it's a polar solvent. If it was a non-polar solvent, everything would change. Everything would change. This geometry, this is also why ice expands when it freezes and contracts when it becomes liquid water again. Most chemicals don't do that. Most liquids, when they freeze, just become smaller. But water puffs up a little bit. And so that gives us things like erosion, which gives us soil. I mean, all of this chemistry happens because of it. I'm not going to say geology because I'm a chemist. I'm going to stake my claim with geochemistry. And I'm not backing down. And so that's what happens. So this is the exception. So we've talked about a lot in this video. It's over 35 minutes already. And that's okay. So watch parts that aren't making sense. It might even make sense to go back to the very beginning, because I just hit you with these line drawings, these Lewis structures right off the bat. And we just rolled with it. And then I showed you how to draw them. And so if you go back, it might make sense to out of that first slide a little bit, first piece of paper. But coming out of this, you should be comfortable with knowing how many bonds an element's going to make. You should also be comfortable knowing how to draw those structures off of that information. So you should be able to take an element, draw the atoms Lewis structure, draw the shared electrons coming off of it with the other atoms Lewis structures, and know how many bonds it's going to make. And then you should be able to know whether a bond is polar or non-polar, like this is a polar bond, and be able to label with a dipole arrow. And then you should be able to expand on that and tell me if a molecule is polar or non-polar. So all of these ideas are completely wrapped together. So you can't tell me if a molecule is polar or non-polar unless you can draw the Lewis structure. And you can't draw the Lewis structure unless you know how to use the periodic table to help you with that. So it's a lot that I've just shown you, but it all goes together. So if you're lost, just take it from the beginning again. Just learn how to draw the atoms, and then learn how to connect them to make a molecule, and then learn how to determine if a bond is polar or non-polar, and then label it, and then see if the labels cancel each other or not, and then you know. Or maybe you don't have to label anything at all, right? Maybe it's all non-polar bonds, in which case you have a non-polar molecule. Alright, so we're going to talk a little bit about ions with one more video in this section. We're going to talk about Lewis structures for ions. Very similar, but also very different. There will be no lines because there are no shared electrons in an ionic compound. This means the electrons are being shared. So we'll elaborate on that more in the next video. But it should be shorter than this one. There aren't as many details, especially since the whole next section is about ionic compounds. So this is kind of a primer for the next section coming up.